Hello students, in this session we are going to start with one of the most important topics of engineering mathematics, which is called as the de Moivre's theorem. Now this de Moivre's theorem is basically based on something called as complex numbers that you have learned in your lower standards. Now what is a de Moivre's theorem and how do we apply it to solve questions is what we'll be looking into this particular chapter. In this chapter, students, there are three different types of questions that we'll be looking into. In the very first type of question, we are going to get formulas. For instance, if I ask you sine 3 theta, so do you recall that sine 3 theta is written as 3 sine theta minus 4 sine cube theta. So here you have expressed sine n theta, isn't it? Sine 3 theta is like sine n theta. So this sine n theta is expressed in powers of sine theta, and sometimes we express it in powers of cos theta. So that is going to be your first type of question where you are going to represent sine n theta or cos n theta in powers of sine theta and cos theta. So that is going to be our first type of question. In the second type of question, the same formula, students, I can modify. I said that sine 3 theta was 3 sine theta minus 4 sine cube theta. So you can understand from here, I can get the value of sine cube theta by doing small rearrangement, isn't it? I can get the value of sine cube theta, and if you observe, the value of sine cube theta will come 3 sine theta minus sine 3 theta whole divided by 4. So in this formula, I have expressed the power of sine in terms of sine again and the multiples of the angle theta. Listen carefully what I said. I said I have expressed the power of sine in terms of again the sine and the angles are multiples of theta. So this is going to be the second type of question where you are going to express the powers of sine theta and cos theta in terms of sine, or you can say cos, and their angles will be multiples of theta. This is going to be the second type of question. And students, the last type of question, the third type, we are going to do something called as the nth root of a complex number. Now you have already learned something called as the square root of a complex number in your lower standards. You must be recalling you have got the square root of a plus ib, isn't it? So here we are going to proceed further to find the nth root of a complex number. So students, you can understand that this entire chapter is entirely going to be based on one single concept, which is called as a complex numbers. So we should be first of all very clear with the basic concept of a complex number. So let's begin what a complex number is. Now you must be recalling that a complex number is usually denoted by z and it is given as a plus ib, isn't it? You must be recalling this. Z is equal to a plus ib, where a and b are nothing but what? They are real numbers. Students, here we are not going to represent z as a plus ib. We will always write z as x plus iy. So now I'm going to start with the definition of a complex number. Now students, do you recall that if you take numbers, first of all, numbers can be categorized into two different types. One is called as real numbers and the other one is called as imaginary numbers. So let's begin from there itself and then we'll come to the definition of a complex number. So if I take numbers can be of two types. One of them is called as real numbers and the other one is called as imaginary numbers. Now whatever numbers that you can count, that you can think of, is called as a real number. For instance, if I say 1.75, this number we can imagine. If I ask you to get me say 150 grams of a certain you can say mango. A mango is weighted of say 150 grams. So you can understand that this 150 grams is a real value, isn't it? There can be a mango whose weight can be 150 grams. Can there be a mango whose weight can be 175 grams? Of course it is possible, isn't it? 174 grams. 234 grams. There can be a mango whose weight can be 234.45 grams also. So all these numbers that I'm talking about are all real numbers. You can count the number of trees, you can count the height of a person, a weight of a person, isn't it? So all these quantities that you can think of, these are called as the real numbers. So the first one is a real number, and obviously the second one, the imaginary number, is nothing but I is equal to root of -1, isn't it? If I try to get the root of a negative number, that is not possible. So that number is called as an imaginary number, and we denote it with I. So I is equal to root of -1. Now students, real numbers can be further classified as rationals and irrationals, although it is not the part that we want to look into, but let's very quickly take this also. So you have rationals and you have irrationals, isn't it? So any number which is expressed in the form of P upon Q, isn't it? P upon Q. So P upon Q form is called as a rational form. So any numbers which is of the form P by Q, and moreover the numbers are either recurring or you can say terminating. So if the numbers are recurring or terminating, then you say that the numbers are rational numbers. Let's take an example. So if I give you 1 upon 2, so this is 0.5, isn't it? So the number got terminated. So this is P upon Q form. The answer came 0.5. The number is terminating. It is called as a rational number. And if I give you 1 by 3, the answer is 0.3333, isn't it? So this number is again of the form P by Q, and 0.3333 is a recurring number. It is never going to terminate. So such kind of numbers are called as rational numbers. And students, the numbers which are neither recurring nor terminating will be called as irrational numbers. So here I can say neither recurring nor terminating. So such numbers are called as irrational numbers. Students, you can recall that E, then pi, root of 2, and so on. These numbers you were taught they are irrational numbers. So you can understand that numbers are basically of two categories. One is a real number and the other one is an imaginary number. So now when you take the real number and the imaginary number and do the addition of them, then you get something called as a complex number. So a complex number is what? A complex number is basically a combination of a real number and an imaginary number. So students, the complex number that you have learned in your lower standards was of something called as the rectangular form. You might be recalling that there is an x-axis and a y-axis in a coordinate system, isn't it? So there is an x-axis, there is a y-axis. So if you take a complex number written as z is equal to x plus iy. So z equal to x plus iy, this is called as the complex number in the Cartesian form, or you can say the rectangular form. So the very first form that you are going to learn about a complex number. So now you know what a complex number is, isn't it? It is just a combination of a real number and an imaginary number. So how do I write a complex number? So complex number, the very first type to understand about a complex number is the rectangular form. We want to understand something called as a rectangular, or we can also call it as a Cartesian form. Now this is the most important one, because from here itself we are going to derive the rest of the forms of a complex number. So as I said, I'm going to draw the x-axis and the y-axis, and the complex number in rectangular, or I can say the Cartesian form, is simply given by z is equal to x plus I y. Now remember, x and y, these are real numbers. So I can say here x and y. So this is very important, students. X and y, they are definitely real numbers. This I is telling us that this is an imaginary part. This is an imaginary part. So this Iy entirely becomes an imaginary part, and this x is called as the real part. So we have an imaginary part and a real part. So remember, I and y together is called as an imaginary part. This entire thing will be called as an imaginary part. So who is telling that this is an imaginary part? The I is telling us it is an imaginary part and x is a real part. And remember that x and y, these individual numbers, these numbers will definitely be only real numbers. The I that is specified over there, this goes and tells that it is an imaginary part. Now students, observe carefully. I'm going to do something called as the Argand's diagram. You have learned all these things in your lower standard, so it's a quick revision of what we have learned. So I'm going to draw an Argand's diagram over here. So this x and y can be positive, negative, negative, positive, both negative. So any values of x and y are possible over here. So the point can go in any of the quadrants. If you take x and y and they are both positive, the point lies in the first quadrant. If x is negative, y is positive, you know it is going to be the second quadrant. So likewise, if both x and y are negative, it is going to be the third quadrant, and if x is positive, y is negative, it is going to be the fourth quadrant. So x and y can lie in any quadrant, so you can have a point in any quadrant. So for simplicity purpose, we are going to take x and y in the first quadrant. So I'm going to draw something called as an Argand's diagram. So let's understand what is an Argand's diagram. So students, I take the x-axis and I take the y-axis, and this is the origin. So let's take a point P. I'm going to take a point P here. This point P has coordinates x, y. We know x and y are both real values. Now remember, this x-axis is called as the real axis and the y-axis is called as an imaginary axis. So we have a real axis, we have an imaginary axis. There is a point P which has coordinates x, y. So we know x is the real part and y will represent the imaginary part when it is written along with an I. So I has to be mandatorily present to denote it as an imaginary part. So now look at this. This point is P. Its coordinates is x, y. So we know that the horizontal distance or the perpendicular which is drawn from point P on the y-axis, so let's call it as say PM. So this is going to be the value of x. This is going to be the x coordinate. And likewise students, if I draw a perpendicular from the point P on the x-axis, it is going to be PN. Let us call it as the y coordinate. So this is going to be the y value, this is going to be the x value. Now I'm going to join this O and P. So let's join this OP. So this OP is now called as R, or it is also called as modulus of Z. So this OP, students, OP is called as R, or you can say modulus of Z. Remember now, Z is always given to us as what? X plus I, Y. So this OP, R or modulus of Z, this is called as the magnitude. This is called as the magnitude of Z. So I can write it as R or mod of Z. Now look at this triangle. You can say this triangle is triangle ONP, isn't it? It's a right angle triangle. So I can say in right, so that's RT angled triangle ONP, I can make use of the Pythagoras theorem, isn't it? The Pythagoras theorem to get the length of OP. So you can see that OP square is going to be ON square plus PN square, isn't it? ON square plus PN square. Now I know OP is R, or I can say modulus of Z. So I'm going to write here R square initially. Now ON, if you observe, ON is same as PM and is taken as X. So I write x square plus Pn, which is y. So I write here y square. So I've got r square as what? X square plus y square. So from here r, or I say modulus of z, is going to be root of x square plus y square. Now, do you know that x is nothing but representing the real part and y is representing the imaginary part when it is present with an I? So here I can say modulus of z is basically under root of real part square plus imaginary part square. So that's the formula for finding the modulus of the complex number. So modulus of z is given by under root of real part square plus imaginary part square. So this is called as the magnitude of z. Likewise, students, there is another very important concept. This is called as the argument, or we call it as the amplitude of z. So you can observe here this angle is measured with the positive direction of the x-axis. Now this is very important, students. You always need to measure the angle with the positive direction of the x-axis. So this is your positive direction of x-axis. You are always going to measure the angle with respect to the positive direction of the x-axis, and it should be in the anti-clockwise direction. This is another very important concept. So this angle is denoted as, say, theta. So this theta is called as an amplitude, or we call it as an argument of z. So remember, it should always be in what? Anti-clockwise direction. The measurement should always be in anti-clockwise direction, and the measurement should always be taken with the positive direction of x-axis. So when it goes in the second quadrant, the angle is going to be more than 90 degrees. When it goes to the third quadrant, it is going to be more than 180 degrees, and when it goes in the fourth quadrant, the angle is going to be more than 270 degrees. So this is very important, students. Whenever you want to tell the amplitude or the argument of z, it should always be measured with respect to the positive direction of the x-axis and in the anti-clockwise direction. So here, students, I'm going to write amplitude. It is called as amplitude, or we call it as an argument of z, isn't it? So it is called as theta. So theta, I'm going to get theta here. Now observe carefully. So before I get theta, if I ask you to get me tan theta in the same right angle triangle, get me tan theta. Now do you know that tan theta is opposite upon adjacent? So here you can say for theta the opposite is y, and adjacent is nothing but on, which is going to be the value of x. So I get y upon x. So I've got tan theta as y upon x. So from here theta becomes equal to tan inverse of y upon x, or I can say tan inverse of what is y, students? Y is nothing but the imaginary part. So I write Im upon Re, the real part. So you can observe here, this entire thing that you have learned was nothing but the revision of what you have learned in your lower standard. So I have taken the very first form. It is called as what? It is called as a rectangular form, or we can say it as a Cartesian form. So z is equal to x plus iy. And two very important things that we have recalled from our lower standards is the magnitude of z, which is given by under root of real part square plus imaginary part square, and we have understood the other concept called as the amplitude or the argument of z, denoted by theta. This theta is nothing but what? It is the angle made by this ray OP, which is nothing but the length r, or I can say mod of z. P is the point whose coordinates are x comma y. X is the real part, y is the imaginary part. So who is theta? So theta is the angle made by the ray or segment OP with the positive direction of x-axis in the anti-clockwise direction. So this theta is given by the formula tan inverse of imaginary part upon real part. So students, in this particular part, we have understood what? We have understood the very first way of representing a complex number, which is called as the rectangular or the Cartesian form. So now we are going to proceed further to represent two more different forms of representing a complex number. So students, let's proceed ahead.